All right, so I think you're on the, what, 6th law in your book now almost? 5th law. So Dalton's law is very easy. It's called Dalton's law of partial pressure because literally we're looking at individual partial, so like an individual gas, the pressure that it portrays. We look at another gas, the pressure it portrays, another gas, the pressure it portrays, and then we just add them up. So I like to call it a summation of partial pressures. So the summation aspect would tell us that in the end we're adding them up. So now you're with me. If you're not done with your quizzes, you're with me now. In your foldable, let's go. Okay. So in terms of our atmosphere, we have a lot of gases that make up the composition of our atmosphere. Who's wondering if you know the most abundant gas in our atmosphere? Corbin.
Carbon dioxide.
No, that would be horrible for our breathing ability. Yes, ma'am. Nitrogen gas, right? But nitrogen makes up about 70% of our atmosphere. Can you tell me another gas in our atmosphere? Oxygen, right? We have to have oxygen. That's definitely in there. Okay. Why am I writing these with a 2? They're diatomic in nature, right? That's their most stable form. CJ Sable, tell me another. Hydrogen. There's probably a little bit of hydrogen, especially just in small quantities. Hydrogen is flammable, so there's not going to be a ton of that because our atmosphere would be burning up all the time, right? Up here, another gas in our atmosphere. Carbon stable. Carbon dioxide. That wasn't me being exhausted with you. That was me giving my as a hint. Okay, because our CO2 production is quite high, especially in America, but the atmosphere is a global atmosphere, so it does kind of get distributed. China does a pretty good job of pumping some CO2 in there too. All right, so there's probably a couple more, guys. Anybody want to name some? Yeah. Argon is an inert gas. I'll put inert here to mean non-reactive. Okay, so that's an inert gas that is present in our atmosphere. One more. Yeah. Say again. Okay, there's probably methane. Okay, so this is going to be like nitty-gritty, where these are in small amounts. There's one more that like helps condense into clouds. No, let's not put that one here. It condenses into clouds and it makes rain. Water vapor. Water vapor is everywhere, and that's why we feel the humidity here in the south. And then who's been to like Colorado and Utah and kind of California, that direction? Okay, do they have a high humidity? Yay or nay?
No.
Totally not, right? It could be 100 degrees and it just doesn't feel that way. It could be 100 degrees here with a 99% humidity and we are dying. Okay, so the water vapor in the atmosphere really does some damage to our ability to breathe. Okay, so all these gases make up our atmosphere, right? So what I could say is, if we're in North Carolina, what's our atmospheric pressure? What's our normal atmospheric pressure? 1 atmosphere, right? So I would say P total, okay, so our total pressure of our atmosphere here in Concord, North Carolina is 1 atmosphere. And that total pressure is the summation of P, meaning partial pressure, of nitrogen, partial pressure of oxygen, partial pressure of hydrogen. You guys gave me a lot, so I'm going to write them all. CO2, partial pressure of argon, partial pressure of methane, and partial pressure of water vapor. So literally all of these gases add up together to equal, for us in North Carolina, 1 atmosphere. So all you do is, if I give you, now this will be a very detailed problem because I'd have to give you 1, 2, 3, 4, 5, 6. I'd have to give you 6 partial pressures, 1 for each of the first 6 gases, and then I could say, okay guys, solve for water vapor pressure. So if you were provided with all the data here except for water vapor pressure and you set equal to 1, you just subtract and get the one that you don't know. Okay, so it's a very simple process. Questions on Dalton's law? What's another name for it? Dalton's law is the partial pressure law, or the summation of partial pressure law. Okay, so we're getting ready to do a lab, and that's about 1 slide. That's it. You guys have an example in your foldable now, right? What's our example? Our atmosphere, global Earth atmosphere, okay? Okay, so I'm going to tell you kind of how the setup will look, and then we're going to get in the lab. It's called the molar mass of butane lab because we are using lighters. So like big lighters, butane lighters. So who's ever like, used a lighter when you strike with your thumb? Okay, so the ones that we have today do not light. They don't combust. I've taken the flint out, so there's no striking mechanism to light the gas. It's just gas, because we want to capture that gas. So if the moment you stick your thumb on there and kind of do the little flick motion, gas just starts to come out. Do not do that in the lab. We want to capture that gas, so what we'll do is we're going to put it underwater, put a little contraption on top, and it will bubble through, and we can see those bubbles. We'll capture that gas. Because if you just do it like this, it's going to put flammable gas in my room, which I really don't want, okay? So, goggles, of course, if you wish, aprons, mainly for Bryce, because he's going to have his apron. Make sure your hair is back. But you'll have a balance, it's right back there. You will need a 100 mil grad seal. Make sure you have one in your cabinet. If you don't, I'll show you where they're in the back. I've already provided the lighters for you. You need a container. Okay, so the container, literally, go ahead and shut your computers because you shouldn't need them anymore. And if you're working with me, you are like on the paper you pulled out for lab, you have it titled already. All it has to be 10 pounds. Write purpose on there because that's how we roll. Yeah, if you want to put your video, you don't want to put your video in, it's not necessarily fine. I know paper shortage here, paper shortage. Okay, so what we're going to do is we're going to have our container, and it's going to be filled with water, probably an inch from the brim, okay? Most of us have like a little handle. You see the buckets around the room? They have a handle, so obviously you can't put the water above the handle or it'll spill out. So what we're going to do is we're going to, in terms of the procedure, you guys obviously can read, but after you do the initial part of the procedure, get your initial masses and so forth, you're going to have your graduated cylinder. You're going to take the bottom off, so the bottom plastic piece won't be there. It'll just be like a clean glass bottom. Here's a graduated cylinder. It's upside down, right? Remember we were doing this like a couple days ago? And our graduations are here. What we're going to do is this is also going to be filled with water so that there's 100% liquid everywhere. After we get to the point where we're good to go, we're going to take our little lighter that we've already masked. We're going to put it in our hand. That's our hand. And we're going to put it underneath the water. Hand and all, okay? Your hand is what's going to flick the lighter mechanism. And when you light it, what's going to come out? Gas, not fire, okay? Because I've taken the flint out. So the bubbles are going to rise in here. And what's it going to do to the water in here? Displace it. So we're hoping we collect bubbles up here. And we're going to collect it no more than 100 milliliters of volume, because the 100 milliliter mark's way down here, right? Okay. If I collect more gas than 100 milliliters, how many milliliters did I collect? Say again? Great, you don't know because you don't know. Okay, so do not go above 100 because then we won't know, and I'll say, yeah, start over because you didn't follow instructions, okay? So after our gas has been collected, of course, it can go all the way down here, no problem. You can collect from 100 down, okay? So it's totally fine with 70 or 60 or whatever. It does tell you specifically to collect where in the lab, tells you to stop where the water level on the inside is equal to the water level on the outside, because we basically want the water levels to be equal so that the pressure of the atmosphere pushing down on this water is the same as the pressure of the atmosphere pushing kind of up on this water. So we do not want to go, we can always move our graduated cylinder, but we don't want to have those unequal. I'll show you how to dispose of butane in just a moment. Do write down this data point. This is currently the pressure, atmospheric pressure in Concord, North Carolina as of like 8 o'clock this morning. Notice that we are Americans, so what are we using? Inches of mercury. It's a shame, but you guys can calculate that you can do the conversion to an appropriate pressure unit. I've provided for you inches and centimeters if you need that conversion for yourself. In terms of what we're going to see present in here, in this little gas tube, what is this supposed to be representing? These big bubbles? What gas in particular am I letting out of the lighter? Butane. This is the title of the lab, right? This is butane. So if this is all butane and it was bubbling up through this water, like bowl of water, what do you think butane maybe carried along with it? Say again? Water vapor, right? All this water is liquid, but it can vaporize. So there's water vapor dispersed throughout the butane. And we really don't care for that. We don't want that included in our calculation. So what we have to do I asked for you guys to shut your computer a while ago with me. Okay? So, what's in here? Either of you. And? Okay, why is the water there? No, that's not why the water's there. The water wouldn't be there if it was displaced. Another reason, it's not water liquid, it's water what? Vapor. So as we allow for the water, the butane to bubble through the water, it carries vapors along with it. Stay with me. So if the vapor is there, we have to account for that. So as you can see, you have to come up to the board and get your water vapor pressure. That's included, but you need to incorporate into your calculations. So I basically have I'll just click it right here. I have a table that tells you the temperature and the water vapor pressure in millimeters of mercury for every individual water vapor at every different temperature. So what do you have to know before you come up here? Say again? The temperature of your system, right? So you have to have that before you can come up here. Okay, and then lastly, the idea is that if you know the overall pressure, this is of course using Dalton's law, if you know the overall pressure, you should be able to incorporate the overall to be equal to the sum of the gas pressure, butane, and the water vapor pressure that you account for from this link. Major questions right now? Major questions? Okay, so it's called Molar Mass of Butane Lab. I'll leave this up here for your convenience. You guys are mostly in your groups now. I need 3 of you guys to stay together, and I'm going to have to boot 1 person out because I got a couple more groups to fill, okay? So 3 people in your table will stay, be a group member, and then we'll switch around a couple more. Let's go. It does not matter because one person is volunteer to Molar mass of butane. Molar mass of butane. This is going to be one last section. Alright. You need to be at a station in 5. 3. Guys can form groups. Good. 2, be at a station. 1. There's an empty station here if nobody has one. Alright, you probably have groups of 3 hexanes because mostly Molar Mass of Butane Lab is out and you're rolling. You guys can carefully fish it or something. No, that was too